So today we're talking about Chapter 3, Section 5, Complex Zeros, and the Fundamental Theorem of Algebra. Yeah, I think this will be good. All right, we'll just read it. So we have already seen that an nth degree polynomial can have at most n real zeros. In the complex number system, an nth degree polynomial has exactly n zeros, counting multiplicity, and so it can be factored into exactly n linear factors. This fact is a consequence of the fundamental theorem of algebra. Right. And this would be the fundamental theorem of algebra. So the following theorem is the basis for much of our work in factoring polynomials and solving polynomial equations. The fundamental theorem of algebra: every polynomial, p of x, polynomial stuff, with complex coefficients has exactly one complex, has at least one complex zero. Okay, so because any real number is also a complex number, the theorem applies to polynomials with real coefficients as well. So what does this mean? That last part down there, because any real number is also a complex number, right? Because we know that we can write a complex number as 3, right? That's 3. 3 can be written as a complex number, right? Because it's 3 plus 0i, right? So any real number is also a complex number, and then this theorem again does apply to real coefficients as well. And of course, we talked about complex numbers in section 1.5. Recorded that lecture. Go back and watch it if you need to familiarize yourself again. One day I said refamiliarize, and somebody was like, "Isn't that the same thing?" I was like, "Yeah, shut up." So there's that. Can I fit that here? No, I cannot. Okay. All right, so the fundamental theorem of algebra and the factor theorem together, the factor theorem is what we did last section. The factor theorem is what I said that many of you will struggle on, and if you I haven't got any questions. I do have a couple meetings with some students, but again, if that's not coming to you very clear, email me, meet with me, we'll talk about it, okay? But anyways, moving on. And the factor theorem together show that a polynomial can be factored completely into linear factors, as we now prove. Now, I didn't actually prepare the proof for you, and I probably should have. But so since I don't fumble around on this, we're just gonna not do it. It's just a proof. But I do like to try to prove important mathematical theorems. But I was unprepared this time, I'm sorry. Okay, so anyways, so example 1. So we need to find all the zeros of P, find the complete factorization of P. All right, so now if we were in the classroom, okay, with each example, I just say, hey, I put it up on the board. I say, hey, do this, okay? And it's really fun to watch, people struggle, right? No, it's really not. But you learn by doing, right? So learning things online is a little bit harder because it's more of a lecture based class now, right? Because it's not a hey, do this and we talk back and forth. But with that said, whenever I let students loose and we try to solve a problem, students, and myself included when I was a student, right, I would try to solve problems the way I have been solving them, right? So I would look at this example and I'd be like, oh, find all zeros, oh crap, right? So I would say, all right, so I would say I would have the factors of 3 over the factors of 1, and I'd proceed from there, right? But it's not that hard, right? Because many times, actually, I'm going to write P of X, many times we get into what I call autopilot mode and try to do the last thing we learned while forgetting everything else that we've learned, right? Because we just assumed that we would use the same procedure that we have learned, right? But that's not the case for this problem. All right, instead, we're going to go right back to what I said a long time ago about if you see 4 terms. Okay. Now, again, this should be the first thing you think, and I didn't do it in the last section. I don't know if there were 4-term equations, but if you see 4 terms, just give this a stab because you can save yourself a ton of time. Okay. So, anyways, we split it down the middle, right? And so we factor the left side. We've got x squared. Right. What remains would be x minus 3. We factored a positive 1 out essentially, right? So we would have plus x minus 3. And then from here we would factor again, so we would have x squared. Yeah. Okay, we'll do x minus 3 and then x squared plus 1. Right. And then it says to find all the zeros. Well, we essentially did already, right? Because this one, right? This 0 is at x equals 3. Okay, but what about this one? Okay, well, this 0 is at x is equal to plus or minus I, right? Because if we took that x squared plus 1 equated to 0, x squared is equal to negative 1, and then take the square root of both sides. That's how I get plus or minus I. Okay. So if I have zeros at, let's see, we'll do it this way. So this is A, and then B. We'll say that we have zeros. That is an E. Well, close enough. Zeros at x is equal to 3 and plus or minus I. Okay. So with that said, that we can do that. We can factor this completely now by, of course, x minus 3 is pretty easy, right? X minus 3, and then we'd have plus or minus I, right? X plus I, x minus I. Okay. So that's what we did. We factored this polynomial completely. Okay. So luckily, if you didn't get enough of last section, I've got good news. We're going to do more of it. Okay. So again, it reads find all zeros. It's a third-degree polynomial. There's nothing I can pull out. I can't factor here or there. I'm going to have to do that factor stuff, right? So here's what we're going to do. So we're going to do the same procedure we did before, but we're going to put it in yellow this time, right? So we're going to do, do you think white over yellow is okay? We're going to say the factors of 4 over the factors of 1. Yeah, white over yellow is okay. And that would be plus or minus 1, plus or minus 2, plus or minus 4, and then all over plus or minus 1. Well, that's easy. It's just going to basically boil down to what? Plus or minus 1. Plus or minus 1, plus or minus 2, plus or minus 4. Okay. Let me mute my phone. Okay. All right, so now we're going to proceed with finding our factors, and I might cheat a little bit. Sorry, that's what I do. All right, so I know it looks like, so I know negative 2 is going to work. Okay, so I know negative 2 is going to work. So I'm going to go ahead and do we'll do 1. We'll start with 1 again just to show how it's wrong, right? So 1 would be x cubed, so that's a 1 for x cubed. There is no x squared, so we're going to put a 0 for x squared. So we got negative 2 for the x value and a 4 for the constant. Go like this. Okay, so we got 1. 1 times 1 is 1. 0 plus 1 is 1, 1 times 1 is 1, negative 2 is negative 1, and then 3. Okay, so we see that 1 doesn't work. So let's try positive 2 here. So a positive 2. Again, bring that 1 down. 2 times 1 is 2. 0 plus 2 is 2. 2 times 2 is 4. Negative 2 plus 4 is 2. 2 times 2 is 4. 4 plus 4 is 8. Okay, we know that positive 2 does not work. Right, so I did a couple of wrong ones, and then just because, you know, I feel like doing all of them right, I'm gonna go ahead and do the correct one now, which would have been, which we said was negative 2. So negative 2. So we have a 1 here. So 2 times negative 1 is negative 2. 0 minus 2 is negative 2. Negative 2 times negative 2 is a positive 4. Positive 4 and a negative 2 is a positive 2. Positive 2 times negative 2 is a negative 4. 4 and a negative 4 is 0. Okay, so this tells me that negative 2 is a factor of this polynomial p of x. So what I can do is I can write this as p of x is equal to, again, the opposite of this sign, right? So it's going to be x plus 2. And then whatever my, shoot, I forgot the word. Quotient. And then whatever my quotient is, and of course my quotient's here. Okay, it's a third degree polynomial divided by a first degree polynomial, so it becomes an x squared, x and constant, right? So this is going to be x squared minus 2x, and then plus 2. Okay, so I'm going to erase that synthetic division there. Because now we have a nice quadratic equation, and quadratic equations are super easy to factor, except this one. All right, so we can't factor this one, but we do have another method, and that would be the quadratic formula. So let's do the quadratic formula here. We know the quadratic formula is the x, and again, we're solving for this. X is equal to plus or minus, let's try that again, so it's negative b, so negative, I messed that up, didn't I? So negative 2, so negative b plus or minus the square root of b squared, so it'd be negative 2 quantity squared, minus 4 times a, which is 1, times c, which is 2. Okay, and we can already see where this is headed. All over 2a, so all over 2 times 1. All right, so if we clean this up, we have a negative 2, so that's a positive 2, plus or minus. All right, so it's going to be square root of, okay, so negative 2 squared is 4, and then so that's 4 minus, and it looks like 8, right? 4 minus 8, so it's going to be negative 4. So square root of negative 4 all over 2. And of course, that can be reduced even further to 2 plus or minus 2i, right? The square root of negative 4 is 2i, right? And then all that's over 2. And of course, this is where I do lose some people, and they're like, well, how did you get that? Okay, so this ends up being 1 plus or minus I. Okay, how do I get there? It's like this. We know that we can essentially split up these fractions, right? We can say 2 over 2, over that common denominator, plus or minus 2 over 2i. And of course, 2 over 2 and 2 over 2 are both 1. Okay, so that's how we got the 1 plus or minus I. Okay, so that would be finding all this. So I'm going to erase this. So my zeros are, protecting yellow last time. So A, my zeros are at x is equal to negative 2 and at 1 plus or minus I. Okay, so that completes A. I'm going to erase all this now. And then B wants us to, what color did I do B on the previous page? That's still okay. So B wants us to find the complete factorization, okay? Well, Again, this is where it's just a little tricky, right? The first one's pretty easy, right? The 0 being at x minus 2, well, that's easy because I mean that's already, we have that, that'd be x plus 2. Okay, now we need to do the prime factorization of this, okay, which is the zeros are located here. Okay, so pay attention. What we're going to do is we're going to split this up into two separate factors, right? But they're both going to start with x minus, right? Because we always take the opposite sign, correct? So it's going to be x minus, and then the first one is 1 plus I, and then the second one is x minus 1 minus I. I was having this problem earlier on this tablet. I don't know. All right. So then we're going to clean this up. So we can say x plus 2, and then this next parentheses, it would be an x minus, we'll write this and then erase it, okay, because I'm running out of space on here. So x minus 1 minus I. Actually, I don't have to fix it, do I? That's it. X minus 1 minus I. And then the last one is an x minus 1 plus I. Whew. And that's it. Right? So let's recap. I had to find the zeros, and finding the zeros, I had to use our factor theorem. Once I got one of my zeros, okay, again, that was at -2. Once I got one of my zeros, I know that my quotient makes this. Okay. And then from there, you could, I mean, if you're able to, you could factor it. This one was not factorable, so we had to use the quadratic formula. We used the quadratic formula to get our zeros at 1 plus or minus I. All right, and then we completed A. That was the end of A. We found all the zeros of P. And then B, we need to find the complete factorization. So basically, to find the complete factorization, just, you know, now we factor it, or now we write it all in factored form. Okay, and then the x plus 2, well, that one's, you know, that was a gimme, right? And then the x minus 1 minus I, well, that it becomes, you know, that is because, rather, this right here, we as an x minus, you know, the 1 plus I, okay? And then this one is because of the 1 minus I. Again, it's an x minus, you know, your 0, okay? So that's how we got that. All right, so zeros and their multiplicities. In the complete factorization theorem, the numbers c sub 1, c sub 2, all the way to c sub n are the zeros of our polynomial. These zeros need not all be different, right? And we've seen that before. Oh, and there's an example here, okay? We've seen that before, right? If the factor x minus c appears k times, again, you know, our exponent in the complete factorization, then we say that c is a zero of multiplicity k, okay? And so we've seen that before, you know, multiplicities, right? You know, this odd multiplicity means, you know, we shoot through the x-axis. The even multiplicity means that we touch the x-axis, right, or tap it. And then, of course, you know, here we have the following zeros. We have 1 with multiplicity of 3, which is the exponent. -2 with multiplicity of 2, which is the exponent. And -3 with multiplicity of 5, which is that exponent. All right. The polynomial P has the same number of zeros as its degrees. It has degree 10, and then it has 10 zeros. Okay, provided that we count multiplicities. Okay, so don't confuse that with the amount of terms we have. Okay, if you recall, a couple sections ago, we talked about a polynomial like of you know, a 10th degree polynomial. A 10th degree polynomial will have at most 9 terms. Okay, don't confuse that with this. If we have a 10th degree polynomial, it's going to have 10 solutions. Okay, so the zeros theorem. So every polynomial of degree n greater than or equal to 1 has exactly n zeros, as we saw above, right? Provided that a zero multiplicity k is counted k times. Basically, it's just repeating what we said, but in a more rigorous, airtight statement. Okay, this is definitely one I'm going to cheat on as well. in terms of the complex zeros, rather. Not complex, in terms of the zeros. Okay, but we will proceed like we would. No, I don't have to do that at all, actually. No cheating involved. I don't have to cheat. Okay, I ain't a cheater. Mainly because I see it now. I almost got ahead of myself. Again, I told you at the beginning of the section, we get into autopilot mode, and I said I even do it, and this is a perfect example of me even getting into autopilot mode. Okay, because I was all ready to get my factors of 48 and put them over 3. I was so ready to do that, but luckily I don't have to, because 48 has a lot of factors. Okay, instead we're going to go back to what we remember, and we're going to factor first. Okay, so what can I factor out of all this? Well, I can factor out a 3x, and that leaves me with x to the 4th, 6 plus 6x squared plus 16. Okay, so even though this is not a quadratic equation, if you see an equation that has kind of like the anatomy of a quadratic equation, you can treat it as such, right? Remember you doing substitution, and of course, you know, let's go and look at this x squared plus. Actually, we'll do this plus 6x plus 16. Okay, so down here in the red is a quadratic equation, and we can, you know, factor it and use the quadratic formula and all that good stuff, right? Well, if we look at the quadratic equation, or a quadratic equation, we see that the middle term is x to the first power, and then, you know, the leading term is x squared, right? It is exactly the square of the middle term, okay? And we see that here as well. X to the 4th is exactly the square of that middle term. So we can essentially treat this as a quadratic equation. Now we could, and for the sake of it, I guess I will, we will treat this as a quadratic equation and do what we did in previous sections. So what we're going to do is we're going to say let x squared be equal to u. Okay, so if we let x squared be equal to u, then we can essentially change this equation. Right, we're using just substitution here. We can change it into u squared plus 6u plus 16. Is that right? Yeah, plus 16. No, I'm so wrong. That is an 8, Sherman. Yeah, it didn't look like it went evenly, so that's supposed to be an 8. Okay, so u squared plus 8u plus 16, and we know that this can factor into, it is a perfect square trinomial, right? So we can factor that into u plus 4 quantity squared, right? Well, at the onset, I said that let x squared be equal to u, so that means I can essentially change this back into x squared plus 4 quantity squared. Okay, so I'm going to erase all that, but this is what I'm going to be, this is the factored form of that, okay, using that u sub that we did before. And for you guys taking pre-cal, going into calculus, you're going to hear u sub so much. And it's going to be exciting every time you do. Okay, so this factors into, we got 3x, and we said x squared plus 4. Is it quantity squared? X squared plus 4 quantity squared. Okay, so find the complete factorization and all 5 zeros of the polynomial. Okay, so the complete factorization, we're looking now at this. Okay, so x squared plus 4 quantity squared. Right? How would I solve that? Well, you know, same procedure as we've done before, right? What we would do is we would set this factor, we would set that factor equal to 0. So we'd say x squared plus 4 squared is equal to 0. Okay, well, obviously, you know, the square root of 0 is, sorry, yeah, square root of 0 is 0, so we'd say x squared plus 4 is equal to 0. Okay, and then we would have I shouldn't have said that, actually. Okay, I shouldn't have said that, sorry. We're just basically setting the, I mean, nothing changes. I just shouldn't have included the squared part. So nothing does change. I shouldn't have included the square. I should have just done the x squared plus 4. Okay, is equal to 0. And of course, this means that we've got what? X is equal to plus or minus 2i. Okay, so we've seen something like that before. So we have x is equal to plus or minus 2i. So what we're going to do here is now rewrite this as 3x, okay? And we're going to have x plus, what do we say, 2i? X plus 2i. And then we'll have x minus 2i. And all that is squared. Okay? And then, of course, we know from our exponent property that, you know, this 2, you know, our power rule essentially, you know, can be, you know, kind of like reverse distributed through those two. So we would say squared. Okay, and that's a complete factorization in all 5 zeros. Okay, because we counted up, right? This is the first degree, second degree, 1 plus 2 plus 2 is 5, and so we have completely factored this polynomial. Okay. Whew. Pretty sure it only gets worse from here. No, actually, this is kind of fun. Okay, this is actually kind of fun. I like these, and it really drives the point home of what the zeros mean. Okay, what they are rather. Let me make sure I didn't pass over anything important. No, not really. Okay. All right, so example 4. All right, so we need to find a polynomial p of x of degree 4. Okay, so it's telling us it's of degree 4 with zeros at I, negative I, 2, and negative 2, with p of 3 is equal to 25. Okay, so what we're going to have to do is, all right, first part's pretty easy, but you wouldn't expect what we're about to do for a moment. Okay, so we need to find a polynomial with degree 4 with zeros at I, negative I, 2, and negative 2. So you would think, and you would be correct mostly if you said, okay, well, you know, at I, so it's x minus I, x plus I, x minus 2, and then x plus 2. Okay, you're right. That's what we would do. And then, you know, if we were to, and I left a space there, and I don't need to right now, but I guess would have helped. Now we'll leave the space there for now. Okay, and so let's go ahead and combine some of these binomials here. So x minus I, x plus I, that's a difference of squares. So that's just going to be x squared plus 1. Okay, and this is x plus 2, x minus 2 is also a difference of squares, so it's x squared minus 4. And if we combine these together, we've got x squared, I'm sorry, x to the 4th, sorry, yeah, x to the 4th. And then x squared, negative 4x squared, and a plus x squared gives me a minus 3x squared. And then minus 4. Okay. All right, so I kind of tried anyways to leave a little space there because this last part here says with p of 3 is equal to 25. Okay. If I were to plug in a 3 into this equation, and let's go ahead. Well, let's go ahead and do it, I guess. Okay. So if I was to plug in a 3 here and here, okay. So 3 raised to the 4th power is 81. So it'd be 81, and then minus 3 times 9, so it's minus 27 minus 4. Okay. So I can tell you right now that does not equal 25, right? So what do? We're kind of lost, right? That's where we need to have a constant coefficient. Okay, and again, this isn't spelled out to you in this section anywhere, I don't believe. No, not really. Okay, so it's not spelled out to you, but you need a constant coefficient. Okay, and that's where I left a little space there. I was kind of giving you a little hint there, right? A, and A, right? So what we're going to do is figure out what that A constant coefficient is, right? So in order to do that, we're given P of 3 is equal to 25. So what we'll have to do here is we'll have to say P of 3. Okay, so we would say, or we would have, A, and then shoot, I guess I wish I would have erased it. I guess so it was 81. I said minus 27, which is 4 minus 4. Okay, so 81 minus 27 minus 4, which is 50. Okay. Right. And from here we can see that if that's equal to 25, sorry, P of 3 is equal to 25, we would have A is equal to 1/2. Okay. And this I kind of set this up kind of weird, so let's actually backtrack it just a tad. Okay. Oh, can't backtrack too. Okay. So I said P of 3 is equal to our polynomial that we have above. Okay. And then I substituted in 3 everywhere. But I also know from here up here that P of 3 is equal to 25, right? So that's why I set that 50A equal to 25. 50A equal to 25, because this is what P of 3 is. Okay, and P of 3 is equal to 25. And then from there we solved for A, and we got A is equal to 1/2. Okay, so hopefully that's not too confusing. So therefore we have 1/2. This doesn't say integer coefficient, so 1/2 x to the 4th minus 3x squared minus 4. Okay, and that's that. Now we have our polynomial P of x, where P of x equal to 1/2 times quantity of x to the 4th minus 3x squared minus 4, and P of 3 will equal to 25 now. Okay. So that's what you do when you see the P of 3 when you are given a value. So I'm going to snip this again and do B. Okay, so find a polynomial Q of x of degree 4. So Q of x of degree 4 with zeros, -2 and 0. So we're gonna again put that A in here, okay? Because I told you before we need to have that A in, that constant coefficient, and we have a 0 at x. Or I'm sorry, -2 and at 0. So I'm gonna go ahead and put the x right here with the A, okay? And then at -2, so it's going to be an x plus 2. Okay, and -2 is 0 of multiplicity 3, so that means I'm going to put that 3. It's going to be cubed. Okay, so hopefully that's not too difficult. And well, we're not given any information regarding this particular polynomial, so in terms of what we can evaluate it at, so we can just simply stop here. So this is a lot easier, isn't it? Okay. Okay, this one looks juicy. All right, so find all 4 zeros. All right. There's more than 4 terms. I'm not even doing that. I can't factor anything. I can't factor anything out. So I'm going to have to do the yield factor theorem. Okay, so it's going to be again the factors of that. I don't even know what that looks like. Factors of 4 over the factors of 3. Okay, and factors of 4 are plus or minus 1, plus or minus 2, plus or minus 4. All over factors of 3, which are plus or minus 1, plus or minus 3. This is going to be awful. I can tell. It's not good. Okay, so we have plus or minus 1, looks like, plus or minus 1/3, plus or minus 2, plus or minus 2/3. And I am not going to cheat this time. Okay, we're going to do this the hard, long way. And 2/3 plus or minus 4. I'm going to regret this, I know. And then plus or minus 4/3. Wow. Okay, so let's begin. Yeah, here we go. So we're going to start with 1. So we got 3, -2, -1. I feel like I'm going to bore you if I just go through each one of these, but I guess it also does help to see a ridiculous problem like this in action, doesn't it? 4, 3, 2, 1. Okay. There we go. 1. So bring that 3 down. 3 times 1 is 3. So we have positive 1, 1, 0, 0, -12, -12. Okay, so we know 1 does not work. So let's try -1. Oh, darn it! I didn't actually see. I could have done the lower bound and upper bound thing, but I erased it. So we'll see. We'll see what happens here. So we bring that 3 down. So we got -3, -5, 5, 4, -4, -16. Sorry, I was thinking 16, and then 12. Okay, so here's what we do. Notice how we have alternating signs. We have positive to negative, positive, negative to positive. Okay, so this tells me that -1 is a lower bound. Okay, so since -1 is a lower bound, then that means I can essentially mark out, and let me just go ahead and erase this real quick before I mark some more. So since -1 is a lower bound, I know that -2 will not work. I know that -4 will not work, and I know that -4/3 will not work. Okay, so this is a good example of how oh gosh, what was it called? Was it Fermat? No. Darn it, I forgot his name. Maybe it was Fermat. I don't know. But a thing we did where we saw that if we have alternating signs, we have a lower bound. If they're all positive, then we have an upper bound. Okay, so we know that since -1 does not work, that's how we can do that. Okay, so we know that positive and the negative doesn't work. Now let's go to a positive 1/3. Okay, so we bring the 3 down. And so, oh, thank you. We're out of fractions already, aren't we? So 1/3 times 3, well, that's just 1. And then it's -1. And we're back into the fractions. So we've got 1/3. All right. And -1 and -1/3 is a -4/3. -4/3 times a 1/3 is -4/9. All right. -4/9. And then 12 with a denominator of a 9, that's 120, 108. So that is right, 108 over 9. 112, golly. -112 over 9. I don't even know if that's right, I'm sorry. Hopefully we'll see. And then that, okay, we can tell it's not gonna be a 0, okay? So we can erase that. And next we'll do a, have I bored you guys yet? We know the, we will do that. We'll just cheat just a tad, just a little bit. Oh, the next one we're going to have to do is a 0, -1/3, okay? So -1/3, matter of fact, the next two we're about to do, right? Because we're going to do -1/3 and then a +2. So we would have hit it eventually, but let's do that arithmetic anyways. Okay? So -1/3, bring the 3 down, it's -1, so -3, it's +1, +1, so it's a 0, negative, I'm sorry, that's 0, -12, -12, +4, and yes, we are there. All right, well, that wasn't nearly as painful as the +1/3, was it? Okay, so -1/3 is a 0. And again, I cheated, but whatever, right? So since -1 is a 0, I'm sorry, -1/3. Oh no, I need to keep my quotient. Okay, so I'm out of room here. So I'm going to really quickly write what my polynomial is with the -1/3 as a factor. Okay, so we know that being in a factor, once I knew that 1/3 was a factor, it becomes, you know, an x plus 1/3, right? And it's being multiplied by the quotient. And the quotient is this, okay? So that'll be a third degree polynomial. So it'd be 3x cubed minus 3x squared. There is no x, so it's going to be -12. -12. Okay, and I guess I don't have to erase anything, do I? All right, so let's, or I don't have to go to the next page. So I will erase this green down here because I don't need it right now anymore. But let's make this a little bit nicer. X plus 1/3. I really hope I didn't copy that down wrong. Although I guess I do just have the book going. That would just be cheating, even more cheating, huh? All right, so let's snip this page, and we're going to do the factor theorem again. So we're going to do the factors of 12. So factors of 12. Factors of 12 over the factors of 3. Okay. So that would be plus or minus 1, plus or minus 2. Luckily, 12 has a lot. Plus or minus, oh gosh, plus or minus 3, plus or minus 4. Oh, those are just ridiculous. Plus or minus 6. All right, that's that. I totally don't blame you if you tune me out, or if you're watching this later, you fast forwarded. Hey, by the way, when you do watch me, and I know I do ramble, you should watch my lectures on 2 times speed. A little pro tip for you. You get through 2 lectures in the time it takes to get through 1. Okay. So what do these boil down into? So let's see, we can boil these down into, looks like, you know, plus or minus 1, plus or minus 1/3. Okay, plus or minus 2, plus or minus 2/3. Run out of room, and it's just looking junky, so I'm just going to start it over, put it down in the bottom here. So let's try that again. Plus or minus 1, plus or minus 1/3. That's a good little 3. That's the best little 3 I've made all semester. Plus or minus 2, plus or minus. Yeah, see, that's what my normal little 3s look like. And minus 3. And I don't have to do 3 over 3 because that's just 1, so that's good. Plus or minus 4, plus or minus 4/3, plus or minus 6. And then I don't have to do 6/3 because 6/3 is 2, and we've already covered that. Okay. So of these, I know that plus or minus 1 does not work because if it was a factor of this, then it would have been a factor of this. Okay. And I already marked off the plus or minus 1. Okay. I know it's not a positive 1/3, okay, because same logic, but also know that's negative 1/3 because I've already factored negative 1/3, okay, and it just so happens, all right, that did this on purpose. It just so happens the next number I would have known would be a positive 2 is a factor, okay, but let's go ahead and do that. How can I do this? Okay, so let's okay, so we'll do 2, and it is a 3, -3, 0, -12. 3, -3, 0, -12. Let's make sure that's okay. I'm looking here, okay, because that's what I'm going to be factoring this into, right? Or dividing this into. I'm sorry, that's what we're dividing this into. So positive 3, -3, 0, -12. Positive, negative 0. Okay, good. Okay, so we bring that 3 down. 2 times 3 is 6. Positive 3. 6, 6, and then positive 12, and then 0. Yay, we're good. Okay, so I know that this now factor, I know that -2 is now a factor, so I can rewrite this equation now as, okay, so we know that x plus 1/3 is 1 factor. I know that x minus 2 is the next one from this. Okay, no, I can't erase it now. Oh well. And then this was a 30 upon 1, so this comes to 3x squared plus 3x plus 6. Oh my goodness. Okay. I know that, and I'm going to snip this. So you guys remember early on when I said, and I was doing a lot from the book. I just snip it from the book. I said, don't worry, guys. When it comes time to do arithmetic, I will be all over it. Well, this is that time because this is crazy, isn't it? Okay. So what letter did we use? All right, this is a p of x. So this is p of x. Okay. And looking here, looks like I can just go ahead and factor out a 3, right? So I can factor a 3 out. So we're going to go ahead and factor this 3, put it out front. So we'll have x plus 1/3, x minus 2. We've got x squared plus x plus 2. All right, and that is going to be an imaginary number. What all do we have to do for this one? Just find 4 zeros. Okay, cool. So we found 2 of them right here. Boom, boom. Okay. The next 2 zeros are going to be doing this in the using the quadratic formula. Okay. But for the sake of time, and since I know that we know how to do the quadratic formula, I'm just going to slap it in my quadratic formula thing. Okay, so my three zeros for this equation, or for this function's polynomial, all right, are x is equal to negative 1/3, which we got with doing the factor theorem. X would be equal to positive 2, again, the factor theorem. And then we have a negative 1/2 plus or minus I on the square root of 7. And there are my very painful 4 zeros. Okay. For the sake of time, I'll move on. If you need a recap, you can always hit rewind. Okay. So the complex zeros come in conjugate pairs. It reads, as you might have noticed from the examples so far, the complex zeros of polynomials with real coefficients come in pairs, okay? So we will actually go and explore that right now. Notice how, you know, the i's, we have a plus or minus I there, right? Same problem. Even when we were given an I, its conjugate was also present as a negative I. Okay, when we have, again, the 2i, the conjugate is negative 2i was present. So hopefully that's really driven the point home, right? So as you may notice, examples far, complex zeros of polynomials with real coefficients come in pairs. Whenever a plus bi is a 0, its complex conjugate is also a 0. Okay, and of course, the complex conjugate, the conjugate zeros theorem basically just restates that. Okay, so similar to a problem we did, or yeah, the problems that we did earlier where we had to find the polynomials. Right. So had we not known about the conjugate zeros theorem, we would be pretty stuck right here, because this is saying find a polynomial p of x of degree 3, okay, that has integer coefficients. So p of x of degree 3 that has integer coefficients, and 0 is at 1/2 and 3 minus I. Okay, so we have a 0 at 1/2, so we're going to write that as x minus 1/2 and 3 minus I. Okay, so we would say x, and then minus 3 minus I. Okay, had we not known our, again, our conjugate theorem, we would be pretty stuck, because we'd be thinking, okay, so if this is a polynomial of degree 3, how do we get that third x? Well, now we know that we take the conjugate of that, right? The conjugate of 3 minus I would be 3 plus I. So we'd say x minus 3 plus I. Okay. And then we would proceed. So let's do this. Okay, so we want integer coefficients. So we're going to go ahead and x minus 1/2. Okay, and it just occurred to me, I probably should have this b, we need to find the polynomial. I should have expanded that out. So that's an error on my part, I'm sorry, because we're gonna have to expand this out, okay? So, well, no time like the present, right? So let's go ahead and start. So we got this a x minus 1/2. Okay, so now I'm gonna do the x minus 3 plus I and x minus 3 minus I, okay? So that would become, well, just gonna start right, x squared minus 3x minus xi minus 3x plus 9 plus 3i plus xi. So a lot of these are going to be canceled, looks like. So plus xi. I'm pretty sure there's a theorem that might be involved here, but I don't know off the top of my head. Minus 3i, and then minus I squared. All right, so, and minus I squared, I'm just going to go and write that as what? So if we have a minus I squared, we know I squared is a -1, right? So we can just simply write that as a +1. Okay, so we've got the x squared up front, okay? And it appears we're going to have the minus xi is going to cancel. The minus 3i and plus 3i are going to cancel. Okay, so we're going to have minus 6i. Ooh, wait a second, I canceled the wrong thing. I think I said it, I just didn't do it correctly. Yeah, here it is, minus 3i and plus 3i. Sorry about that. Okay, and so it's a minus 6x and then plus 10. Okay, so we have to proceed with this on the next page. So we're going to distribute this x through the trinomial here. So we're going to have x cubed minus 6x squared plus 10x, and then minus 1/2 x squared plus 3x, and then minus 5. Okay, can we combine any like terms here? X cubed, so minus 1/2 x. Golly, even I'm bored to tears right now. I'm sorry. You took this class. It's your fault. Oh no, I messed up the x squared. I forgot. I didn't see that 6x squared. So 13/2. We're almost done, guys. All right. Now, at this point, we would think we're done, but we're not. Why? Well, because we haven't actually figured this a out yet, okay? Because we can't just have that variable there, okay? But we're told what it needs to do. All right, this example says, find a polynomial of degree 3, okay? So we got the degree 3 part down, great, that's good. That has integer coefficients, okay? So meaning that the leading coefficients here, okay, so here that's a 1, here it's a -13/2, here's 13, and here is a 5, okay? We need to have integer coefficients, meaning we need to have whole numbers, okay? So with that being the case, apparently this a probably needs to be a 2, right? Because I distribute a 2 through, and I can take out that that fraction there, okay? So if I made that a 2, then I would have 2x cubed minus 13x squared plus 26x minus 10. And that's that one. Okay. The last thing, and this is the easiest one so far today. Okay, so this one should be a breeze. So if your brain is mush, you're doing good. You're doing good. Or is it well? You're doing well. You're doing good. You're doing both. We have seen that a polynomial factors completely into linear factors if we use complex numbers. If we don't use complex numbers, then a polynomial with real coefficients can always be factored into linear and quadratic factors, okay? Linear, again, being a line, being a first degree polynomial, right? X, right? Just simply an X. And quadratic, of course, being X squared. We use a property in section 10.3 when we use this property in section 10.3. I don't know if we do 10.3, I'm sure we do. A quadratic polynomial with no real zeros is called irreducible over the real numbers. Such polynomials cannot be factored without using complex numbers. So this is something we know, right? It's just now we're putting it into words. So every polynomial with real coefficients can be factored into a product of linear and irreducible quadratic factors with real coefficients. Again, same thing that we've known. And this is, I'm sure, the last example. Okay, so let p of x equal to x squared plus 2x squared minus 8. So we need to factor p into linear and irreducible quadratic factors. Okay, so that's not going to be hard because we know that this, again, we could do the u sub, but I feel like something like this you can actually just really do in your head, right? Just replace the x squared with like an x or a y or something, right? So this factors into x squared minus 2 and a positive 4. Okay, so if, we can reduce that, right? But we can also take the step further, okay? Because we know that this is a difference of squares, so we can say x plus the square root of 2 and x minus the square root of 2. Okay. All right, so that is factoring in linear and irreducible quadratic factors with real coefficients. Done. Okay, and then B, we need to factor completely into linear factors with complex coefficients. Well, that's not hard at all because you know, let's actually go ahead and lead off with the square roots, right? So x plus the square root of 2, x minus square root of 2. And then this would be the complex part, right? But we know that's just going to be plus or minus 2i, right? So this is x plus 2i, x minus 2i. And boom, we're done. We have factored it completely into linear factors with complex coefficients now. Okay. And again, I'm pretty sure that, yeah, that does complete today's lecture.